All right, so we came up with the Cartesian product of the two sets here, A and B, and we did it in both orders, A with B and then B with A. And one thing I mentioned in the previous video was that even though these two sets are different, they're not equal to each other, they do happen to have the same number of elements. They both have 6 elements. Is there a way to predict that these would have had 6 elements without having to list the elements out? The answer is yes. Take a look at this first example right here. This is, these two ordered pairs are the set of all ordered pairs that I could have gotten in this Cartesian product by using a 1 as my first component. Okay? And there were 2 pairs that I could have made here. Over here, there was another 2 pairs that I got by looking for only the ordered pairs starting with a 2 in their first component. I picked the 2 from B and then exhausted my options for my second components, A and B here. Finally, there were 2 pairs that I was able to choose that had a first component of 3 here. Okay? Now, why were there 2 pairs in each of these cases? Where those 2 pairs were determined by the total number of choices that I had for my second component. But those number of choices were just the number of elements that were in set A. And why did I end up with 3 of these groupings of 2 pairs? Well, those were determined by the number of first components that I was able to choose. 2 pairs with a 1, 2 pairs with a 2, 2 pairs with a 3. So that means I had 3 groups of 2, or 3 times 2, which equals a total of 6 elements in total in that Cartesian product. That suggests a relationship that happens to be true for any Cartesian product. If I want to know how many elements are going to be in the Cartesian product of one set with another, all I need to do is take the number of elements in one of the sets and multiply it to the number of elements in the other set. 2 elements in A, 3 elements of B in B, 2 times 3 is equal to 6. Okay? So here is that rule stated a little bit more formally and symbolically. If A and B are 2 finite sets, meaning they have only a finite number of elements, then the number of elements, remember this is the notation that we use, n of, the number of elements in the Cartesian product of A with B is equal to the number of elements in A times the number of elements in B. So here's an example where we can practice this. A is going to be this set here, containing -5, -4, -3, -2, -1, 0, and 1. B is going to be the set of vowels in the English alphabet. I want to determine the number of elements in the Cartesian product of A with B. Okay? So let's actually start by listing B out. B is the set containing A, E, I, O, U. I know some people like to say sometimes Y, but technically Y is not a vowel. So B only has these 5 elements. How many elements are there in A? 1, 2, 3, 4, 5, 6, 7. So the number of elements in the Cartesian product of A with B is equal to the number of elements in A, 7, times the number of elements in B, 5. That's equal to 35. Notice how much faster we can arrive at an answer there compared to if we actually tried listing all of the elements in that Cartesian product. That would be way too time consuming, and that's the value of what we try to do a lot of the times in math. What you have here is what we call kind of the primitive approach. Not saying that you're a caveman if you're taking that approach. What I'm trying to say is that you're using what are called first principles. You're just using the definition of a Cartesian product to try and answer a question. But in math, we look for patterns in things, and from those patterns we try to derive rules and techniques that make problem solving much, much easier and much more efficient, not advanced. This is far more efficient than listing out 35 elements and then trying to count them. Okay. Last thing I want to talk about, and I had briefly mentioned this in one of the previous videos from this section, something called De Morgan's laws. De Morgan's laws are a really handy result in set theory, and we're not going to prove them because that's better left for a more advanced course, but we will illustrate one of them with a Venn diagram on the next page. But here's basically what De Morgan's laws are. If you have two sets, A and B, De Morgan's laws tells us how complements interact with unions and intersections in a specific way. So if, here's one of De Morgan's laws. If we wanted to take the complement of the intersection of two sets, meaning we do the intersection first, and then we take the complement of whatever that result is, then that resulting set is the exact same thing as if we were to take the complements of A and B first, and then take the union of those two sets. So in other words, you can kind of think of this as like a bizarre sort of distributive property. It's not. It's technically not the distributive property, but it has sort of a similar feel. If you think of that little apostrophe there that represents the complement as distributing into the A and the B, so that we get an A complement and a B complement, that works provided that you flip this symbol over and turn that intersection into a union. The same thing happens if this is a union instead of an intersection. We can think of distributing that complement in and flipping the symbol over to become an intersection. A complement intersect B complement is the same as this. Again, not going to prove that formally, but we want to wrap this section up with an illustration of one of those two laws using Venn diagrams. The way that we're going to do that is create a Venn diagram for this set and then a separate Venn diagram for this set, and showing that they end up looking like the exact same thing. So here is one of those. Here's my universe. That's going to be A, that's going to be B, and I'd like to represent the set A union B and then complement the whole thing. So what is the complement of A union B? We've dealt with this before. Remember, A union B as a Venn diagram would look like everything from both A and B shaded in. The complement would have to be everything outside of those regions then. This would be the complement. Okay? What about A complement intersected with B complement? Okay? Universe A B. I'm going to use the ones and twos approach for this one. A complement is the set of everything in the universe that's outside of my set A. And I'm going to put ones for any region that belongs to A complement. So everything out here is outside of A. That gets a 1. Everything that's inside of B but outside of A also gets a 1. So the combined ones here would represent A complement. What is B complement? Well, B complement would consist of everything that's outside of B, which would also include this region that's outside of both sets, but also that little region right there is outside of B. The stuff inside A that's outside of this overlapping region is outside of B as well. So the ones and the twos correspond to A complement and B complement, respectively. Now, if I'm supposed to take the intersection of those two sets, then I'm looking for only the regions that have both a 1 and a 2 in it at the same time. But only one region that I wrote numbers in has both a 1 and a 2 in it. It's this region out here. All this stuff. Okay? Compare these two Venn diagrams. They're identical. Both of them consist only of the regions that are outside of both circles. Okay? So this is not really what we would consider a proof, formally speaking, but it visually shows us why one of the two De Morgan's laws should be true, because we end up with the same region. You can try demonstrating the other of De Morgan's laws, which we would get if we swapped the union and intersection here in a similar way, but I'm going to leave that part to you. That wraps up section 2.3.